All right. Hello and welcome. In this example, we are going to look how to determine the voltage between points A and B on this circuit here. And so the first thing we need to do is figure out what exactly is points A and B. And so we see at point B, we're actually at ground. So point B we know. Point B is equal to 0 volts. Right? So that means that the actual potential that we're looking for is just node A's voltage, right? VA. And when we look at node A, we can see that there's a couple things happening here. Node A travels down through C3 to get to node B. We know node B is ground, right? And that means that that C3 is in parallel with wherever else node A can take us. And we see that that goes through C4 and C5 to get to ground also. So we know that node A's voltage actually is shared here. C3 is in parallel with C4 and C5. Right? So that is what we want to know the voltage drop across. We want to know this is our RA resistance. Well, in this case, it's going to be CA, right? Capacitive. All right, so that means that we can determine that and use that in our voltage divider equation because we want to know the voltage at node A after it comes across C2. Right, because that's our series component there. And if we look back through our circuit here, we'll see that some of our CT doesn't actually matter for what we're looking for here. We have 16 volts at our entry, and we see that that comes up, and our current would divide down C1 and C2, where our voltage is given the same. 16 volts goes to C1 and 16 volts goes to C2. Since we're looking for voltage, we really don't care about that current drop. So we're going to ignore C1. We're going to say that the voltage that we want to know about is just the 16 volts that leads towards C2, C3, C4, and C5, right? Which means the only thing we really haven't accounted for in this equation is just C2. So we'll account for that in our total series capacitance. We'll say that our CT, ignoring the fact that C1 gets a voltage, because that does not go, it's not the voltage that we're dividing into, right? So we'll say CT, from our perspective, is equal to C2. We have no choice but to go through C2 to make it to the next stage of the circuit there. That enters into our VA condition, which we know the total resistance at node A there. So we'll say C2 is in series with our C3 in parallel with C4 and C5. Right, so we want to make sure we do the series components first, and then we'll put those into our parallel of C3, and then we'll put that in series with C2. Right, be really cautious of the series versus parallel capacitor equations. All right, so let's start off with our innermost parenthesis. That's C4 and C5 together. We'll combo those, and we'll say that we have 1 over C4 in series with C5. We see that all of our C values are 25 microfarads, and so we can actually do our other combination, right? We know that if we have 25 microfarads, we can divide by the number of capacitors we have in series, in this case 2, and that's going to give us the total series capacitance of those two components. So now we know that it's not C4 plus C5 at the back end here. It's actually going to be 12.5, and that's in microfarads, right? We'll bring down the rest of our equation. That's in parallel with C3, and that's our next stage here. And then we'll put that in series with C2, and that's going to equal our CT. Right, so we'll keep going here. We'll say that we have our 12 microfarads in parallel with our C3. We know that's 25 again. So we'll put that into our parallel equation. We know that's just summing them together, right? So we'll say that we have 25 microfarads plus 12.5 microfarads, and that gives us a total parallel capacitance there. So we'll say that we now have a CT is equal to C2 in series with 37.5 microfarads. And so we can keep going on this one more time. We'll put that into the 1 over equation here because they do not match. We'll clear this out. We'll say that we have our final series capacitance right here, 1 over C2. We know that's 25 microfarads still, plus 1 over the capacitance we have right now, which is 37.5 microfarads. They're both in microfarads, so we can leave that off and know that this answer is still in microfarads. So we have this equals 15 microfarads. Okay, so that works out for us. All right, so now we can use what we just learned also. We know that if we were to do this red equation up here, we would end up with 37.5 microfarads, right? So now we know CA is equal to 37.5 microfarads. Right? We did that in process of solving for our total capacitance for this side. So now we can apply our voltage divider rule, because we know we have a series component here, a couple of them, and so that's going to take some of our voltage. We just want to know 2VA, so we're going to use our voltage divider and say that we have CA as what we want to know our voltage across, and we'll divide that by the top of our CT. So we'll say CT divided by CA multiplied by our voltage source of 16 volts, and that's actually the voltage leading into this node here at the beginning. And we know both of those values, so we can plug those in and say that CT is 15 microfarads, and CA, we know because we've calculated that in process of our CT, is 37.5 microfarads multiplied by 16 volts, and that's going to give us the voltage drop across VA. So we'll say 15, micro and micro are going to cancel, so divide that by 37.5, and we can multiply that by 16, and that's going to give us 4.6 volts, or 6.4 volts. Right, and that is the voltage at node A up here, 6.4 volts. That means that C4 and C5 both get 6.4 volts that they're going to share, and C3 gets a voltage drop of 6.4 volts because of this node voltage. All right, let us know if you have more questions.